Chapter 2, Intelligent Agents. In this chapter, we will talk about how to design intelligent agents and what are the considerations that we have to make when designing intelligent agents. We will start with the definition of an agent. Earlier, we discussed about agent, but we didn't provide a specific definition about agent. Here, we will define agent specifically for the purpose of designing intelligent agents. An agent is anything that can be viewed as perceiving the environment through sensors and by acting on the environment using actuators. So if this is our agent, let's say here's our agent, then for an agent to be an agent, for the purpose of designing intelligent agents, we define agent to perceive the environment. If this is our environment E, then the agent will perceive the environment using sensors, and it uses something known as actuators to take actions on the environment. So when defining agent, it is extremely important that we mention about environment, mention that the agent has sensors, and also that the agent has actuators to act upon the environment. And this diagram shows how an agent interacts with the environment through sensors and actuators. It is also important to note that sensors and actuators are the part of the agent itself, whereas the environment is outside the agent. The environment is where the agent interacts and acts on. Now, as examples of agents, the human agent has eyes, ears, and other organs as sensors, right? So if this is a human agent, then the sensors for the human agent will be these that can be used to perceive the environment. And hands, legs, vocal tract, etc. are actuators, and that's what we use to take actions on the environment. Another example is a robotic agent. For a robotic agent, cameras and infrared rangefinders can act as sensors for the robot, and various motors can act as actuators. For example, if you have a self-driving car, then wheels and various motors that the robot had can be used as actuators to act upon the environment. Another example is a software agent. A software agent can, for a software agent, its sensory inputs can be the keystrokes it receives, file contents, network packets, and then it can act upon the environment by displaying on the screen, writing to files, and sending network packets, and so on. When talking about agents and how agents perceive the environment, it is important that we understand the difference between a percept and a percept sequence. So a percept is an agent's perceptual input at any given instant, at one instant of time. So say, for example, if we have a robotic agent, then what does the robotic agent perceive at one single instant of time? That is, what picture it is viewing, or what from infrared sensor it is taking from the input, and so on. So percept is the input at a single instant of time, whereas percept sequence is a complete history of everything that the agent has ever perceived. So if we are talking about, let's say, the human agent, then the percept sequence will be everything that the human agent has ever received through his or her eyes, ears, and other sensory organs since the birth of that human. When talking about agents, it is also important that we understand the difference between two things: agent function and agent program. So say you are given a new agent, right? We don't know what the agent does. So here's your agent. We don't know what the agent does, and we would like to know what the agent does. In other words, we're looking for something like an instruction manual for the agent, right? Now, the instruction manual for the agent can be written or described at two levels. One level is to describe something known as agent function, and the other is to describe something known as agent program. To better describe these two, let's take an example of something known as a vacuum cleaner world. Say we have a vacuum cleaner agent. Here's our vacuum cleaner agent. Vacuum cleaner agent. And the problem that we have is we have two rooms, room A and room B, two rooms. And these like in a stone-like things represent dirt in the room. So room A may be dirty and room B may be dirty, and room A may be clean and B may be clean, and so on. So our vacuum cleaner agent has to go to either of these two rooms and suck this dirt, that is, clean these rooms, room 2 and room A and room B. So in this vacuum cleaner world, we just have two locations. One is square A and square B, or room A or room B. And what we have is a vacuum agent which can perceive two things, which can perceive which square it is in and if there is a dirt in the square or not. So this vacuum cleaner can only perceive two things. One, it can perceive which room it is currently at, and second, it can perceive whether that room has dirt or not, right? And as actions, the vacuum cleaner agent can either move left, move right, or suck up the dirt, or do nothing. So the agent has these choices. In other words, this is how it can interact with the environment. So agent function is simply something like a tiny instruction manual that says, here's, let's say, situation, and here's the action. So given this situation, what will the agent do? Given another situation, what will the agent do? Given a third situation, what does the agent do? So this table of all possible situations or scenarios where the agent may receive input and the corresponding actions is agent function. So for the vacuum agent, the agent function will look something like this. If the current square is dirty, then suck the dirt. Otherwise, move to the other square, right? So it characterizes what happens in various situations. If it is in room A and the room is dirty, then the vacuum will suck the dirt. If it is in room A and the room is clean, then the vacuum will move to the other room. And it will keep oscillating until all rooms are clean. So this is what agent function would represent for the vacuum agent. Specifically, I can represent the agent function for the vacuum cleaner agent using a clean table like this. So the first column is the percept sequence, and the second column is the action that we want the agent to take, or the action that the agent takes. If the agent is in room A and the room is clean, then the action that the agent will take is going to the right. If it is in room A and the room is already clean, then obviously the vacuum agent will move to room B to check if it is clean or not. If it is in room A and the room is dirty, then the vacuum cleaner agent will suck the dirt. And this is what we expect. In other words, this is like your instruction manual of this vacuum cleaner agent, right? And if it is in room B, the room is clean, the agent will move left. If it is in room B and the room is dirty, then the agent will suck the dirt. If it is in room A and the room is clean, and if the vacuum cleaner agent continues to stay in the same room, and if it is in room A and now again the room is clean, then the agent will move right. Similarly, if it is in room A is clean, if it continues to stay in the same room, and if it is in A and clean, and after some time it is still in the same room and the room becomes dirty, then the agent will suck the dirt. So this table is basically agent function. We are characterizing what the agent does in the form of this table. Now, agent program is more like the underlying working mechanism of this agent. It's basically the implementation of how the agent works. And here's a very simple implementation of the vacuum agent that we are working with. So it's a function that takes as input the current location and the status. That is, whether it's in square A or square B, and whether the square is dirty or clean. And at the end, it returns an action. The possible actions that it can take is either moving to right, or sucking dirt, or moving left, right? So if status is dirty, then no matter what room you are in, what we will return is the action will be sucking the dirt. Else, if the room is not dirty, that is, if the room is clean, then if it is in location A, then we would want the vacuum cleaner agent to move right. If it is in A, then we want it to move right. And if it is in location B, then we want it to return moving left. Right. So this function, tiny function, is the agent program for the vacuum cleaner agent. So given a new agent, we can use agent function and agent program to characterize what the agent does. So say, for example, you have a new agent, you don't know what this agent does, right? Then what we want to see is agent function and agent program of this agent, so that we have a better understanding of what the agent does given various scenarios. So agent function describes an agent's behavior by mapping any given perceived sequence to an action, as we saw in the table earlier. To describe any given agent, we have to tabulate the agent function, and this will typically be a very large table, potentially infinitely large table, because we have to list out every possible scenario in which the agent may be exposed at and the corresponding action that the agent will take. And we can, in principle, construct this table by trying out all possible perceived sequences and recording which actions the agent does in response. So once you have created or built an agent like this, we expose the agent to all possible environments or all possible perceived sequences that the agent can perceive, and then record what the agent does, that is, what actions the agent takes for these perceived sequences, and then create a table, and that gives us the agent function. So this table is an external characterization of the agent. In other words, here we are ignoring the details of the agent, that is how the agent performs, what program is written inside, and rather we are looking at more abstract mathematical description of the agent. That is, we are looking at it from the outside world and observing the agent and recording what that agent does in various scenarios. The agent program, on the other hand, is an internal implementation of the agent function for an artificially intelligent agent. Now this is a concrete implementation, particularly a program, a computer program that is running within some physical system, either within a computer system or something similar. In the previous chapter, we learned that one of the best definitions for AI is designing agents that act rational, right? Now, how can we define this acting rationally so we can write computer programs? Because eventually we can talk about acting rational and we can talk about many definitions of AI. Ultimately, within computer science, our goal will be to write computer programs, implement or write programming codes that we can eventually show or prove that what we have built acts rationally or does rationally. So how can we define acting rationally? That's one question that we will discuss. Also, when talking about acting rationally, should we consider the environment where the agent will be deployed, or can we define acting rationally by ignoring the environment? So a rational agent, in general, this is just in general, is the one that does the right thing. So this is in general. In general, a rational agent is the one that does the right thing. In other words, every entry in the table for agent function is filled out correctly. So given this circumstance, the agent will do this, and this all needs to be filled out appropriately, correctly. Let's say appropriately. Now, this is not a definition of a rational agent, but it's still, in general, a rational agent is something that does the right thing. So, what does it exactly mean to say that an agent is a rational agent is the one that does the right thing? So, to understand this, what we need to look at is we need to consider the consequences of the agent's behavior. When an agent is plugged down in an environment, it generates a sequence of actions according to the percept it receives, right? Say, for example, we build a new agent and I throw it to a new environment. Let's say, for example, a populated environment like this. It will take a lot of actions based on what it perceives. It might keep walking in the street, or it might start hurting people or helping people. It might start doing certain things. These sequence of actions causes the environment to go through a sequence of states. In other words, because now this agent is acting on the environment will face some consequences or changes. There will be changes in the environment. If this sequence of environment is desirable, then we can say that the agent has performed well. In other words, we have narrowed down this general definition of rational agent or rationality to something that makes more sense. In other words, now what we are saying is this agent may have its own agent program. It may have its own agent function, right? Which may be really good on their own. But what we are looking at is when this agent acts on this environment, what consequences happen to the environment? What changes happen to the environment? And are these changes desirable? If these changes are something that is desirable, then we can say that this agent is rational. Otherwise, even though the agent program may be good and the agent function may be good, if the impact on the environment is not desirable, then we can say that the agent is not acting rationally. So the point that we are making here is we are interested in environment states, not agent states. In other words, the agent may be doing many things within itself, but we are not concerned about what happens inside the agent. Instead, what we are concerned about is what happens to the environment. This is what we are more concerned about. So, we should not define the success of an agent in terms of the agent's opinion. The agent could achieve a perfect rationality simply by deluding itself that its performance was perfect. The agent might say, this is what I was designed for, I did exactly what I was supposed to do, but the impact on the environment may not be very good, right? And human agents, for example, are very notorious for sour grapes, right? So if you cannot reach out to, or if you can finish a task, or if you don't achieve something, we always make very good excuses by saying that there were some other reasons for us not being successful or not achieving what we really needed to achieve. So, in other words, what we want to do is define rationality in the context of the changes to the environment rather than the changes to the agent itself. So the performance measure that we define, in other words, our evaluation metric to evaluate how good our agent is or how bad our agent is, should focus on environment rather than what the agent should behave. So when we are designing new agents or creating or building new agents, we should design our performance measures according to what we want in the environment rather than how the agent should behave. Because we may go on and spend a lot of time trying to decide what the agent should behave and what the agent should do, but ultimately what matters is the impact on the environment. So our performance measure should be based on what we want in the environment. For example, for the vacuum agent that we had, we propose to measure the performance by the amount of dirt cleaned up in a single 8-shift hour. Let's say we have the vacuum cleaner agent, right? Agent. And what we want to do is design an agent that can clean as much dirt as possible. That is, we are trying to, our performance measure to evaluate how good the agent is this. We want to check the amount of dirt cleaned up in an 8-hour shift, right? Now, this looks like a really good performance measure to evaluate or to check how good the agent is. But there's something wrong with this performance measure. And here's what's wrong. What the agent might do is, in the first second, collect some dirt, and then in the second second, throw it back to the environment. And then pick it up again and throw it back to the environment and pick it up again and repeat this over and over again. So in 8 hours, the agent will have collected a lot of dirt. If you measure the amount of dirt that the agent collected, it will have collected a lot of dirt. But it's collecting more dirt because it's throwing the dirt back to the environment. In other words, this definition, although it looks a really good definition of evaluating our vacuum agent, doesn't take into account all the possible impacts on the environment, right? So this is an example where our performance measure should be designed such that it addresses exactly what we want in the environment. So overall, what is rational at any given time depends on 4 things. The performance measure that defines the criteria of success, the agent's prior knowledge of the environment, the actions that the agent can perform, and the agent's perceived sequence to date. Now, we are getting into really tricky, defining rationality in a really tricky way. So, say for example, we design a vacuum cleaner agent, let's say our vacuum cleaner agent, and our performance measure is like the one before, that is amount of dirt cleaned, right? So this is our performance measure. So let's say we design a vacuum cleaner and this is our performance measure, and what the vacuum cleaner does is it collects dirt, throws it back to the environment, collects more dirt, throws it back to the environment, and oscillates cleaning the dirt. Then this vacuum cleaner agent is rational. It is rational. It is rational. It is not irrational because it binds to our definition of performance measure. In other words, it meets our performance criteria. So what is rational depends on what our performance measure is. Rationality also depends on the agent's prior knowledge. Say for example, we have a lot of rooms, just like room A and room B, where we have room A, B, C, D. And let's say there's a vacuum cleaner agent that comes to room A, tries to clean the dirt here, even though there is not dirt, goes to room B, again cleans the dirt, goes to room C and again cleans the dirt. So based on how we define, based on what the agent already knows, it may be rational for the agent to suck the dirt in every room because it may not know that every room is not clean. Also, rationality depends on what actions the agent can perform. So if you're let's say we have a square room that the agent has access to and the agent is supposed to clean, and let's say the agent cannot clean the corners. In other words, physically the agent is not capable of cleaning the corners. So then it is rational for the agent to not clean the corners because it cannot perform such actions, right? So rationality also depends on what the agent can perform. It also depends on the agent's perceived sequence to date, that is, what the agent has learned over time. So now let's look at a formal definition of a rational agent. How can we define an agent that is rational? For each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure. This is the most important part. Maximize its performance measure given the evidence provided by the percept sequence and whatever built-in knowledge the agent has. Now, you may be thinking that a robot is good. Let's say a robot is good if it saves humanity, right? But this is not true, because in the definition of rational agent, what we are saying is an agent is rational if it tries to maximize its performance measure. It doesn't say either save humanity or harm humanity. An agent is rational if it does what it's designed to do. If it is designed to hurt people, and if the agent exactly does that, then we say that the agent is rational. If it is designed to save humanity or save people in various circumstances, and if it does that, then once again we call that agent as rational. We can have pre-loaded knowledge into the agent, or the agent may go through a percept sequence and learn something about the environment to act upon the environment. But what is rational depends on what performance measure that we use. So an agent is rational if it maximizes, or if it tries to maximize the performance measure that it is designed for. Here's an example that demonstrates the problems with performance measures. Let us assume the following for the vacuum cleaner example. Let's say our performance measure is this. We award 1 point for each clean square at each time step over the lifetime of 1000 time steps. That is, every time the vacuum cleaner agent makes the room clean or perceives the room as clean, we award it 1 point. The prior knowledge that the agent has is there are 2 squares, but it doesn't know the dirt distribution. That is, every time either of these 2 rooms can be dirty or clean. The available actions are left, right, and sucking the dirt, and the percept sequence is simply that the agent correctly perceives its location and whether the location contains dirt or not. So here is what the vacuum cleaner agent will do. It cleans a square if it is dirty and moves to the other square if it is not, right? So every time it goes to a new square, it will try to collect that 1 point if the room is clean, otherwise it will not. Is this vacuum cleaner agent rational or not? So the performance measure is that every time it cleans a square, it gets 1 point. So to get that, it cleans a square if it is dirty and then moves to the other square. So it definitely tries to increase this performance measure. It uses the prior knowledge, it uses all the actions available, and it perceives percept sequence correctly. So now clearly the vacuum cleaner agent is rational because it tries to maximize the performance measure. The question is the performance measure robust? That is, our criteria for evaluating the rationality or evaluating how good our vacuum is, this correct, or is this good enough or not? That's the question. So here's a problem that can happen. Once the agent cleans up all the dirt, what does it do? It'll oscillate back and forth. In other words, it'll go to room A, clean the dirt, go to room B, clean the dirt, come back to room A and go back to room B, and keep oscillating between room A and room B almost forever, whether the rooms are clean or dirty. But still, the agent will be rational because it still tries to maximize the performance measure. We didn't explicitly say that the agent should not oscillate, right? So here the problem is with the performance measure. That is, the agent is rational, but our performance measure is not good enough to capture what we want in the environment. So to correctly specify what an agent should do, our first step must be to specify something known as the task environment as fully as possible. So what do we mean by a task environment? A task environment is a combination of four things. One is the performance measure, another is specifying the environment, another is actuators that the agent may have, and then listing out the sensors that the agent must have. Here's an example. A fully automated taxi, let's say we would like to design an agent that is basically an automatic taxi driver, right? This is an extremely challenging task to design a fully automated taxi, but before we design this agent, we need to list correctly the P's of this agent, for this agent. So our P, performance measure, will be something like the taxi has to be safe, it has to be fast, it has to be legal, it has to give a comfortable trip, it has to maximize profits for the owners, right? Owners. It also should work in all weather conditions. So these are our performance measures. The environment will be, the agent will interact with the following environments: roads, other traffic, pedestrians, and customers, and so on. The actuators available for the agent are steering, acceleration, brake, signal, horn, display, and the sensors that the agent has to perceive the environment are cameras, GPS, odometer, accelerometer, engine sensors, keyboard for a person to interact, and so on. So when designing agents, it is important that we specify these four things: performance measure, environment, actuators, and sensors for the agent, so that this can then be further used to either make an agent function or an agent program Here are some more examples of correctly specifying a task environment. Say, for example, we have an online medical diagnosis system. Let's say, for example, a WebMD, right? So then the agent type is a medical diagnosis system. The performance measure will be something like healthy patient and reduced costs, not correct diagnosis. Because there may be examples where the agent may do correct diagnosis, but that may not lead to a healthy patient. The environment will be patient, hospital staff, and so on. For a satellite imaging analysis system, correct image categorization may be the performance measure. For part picking robot, the percentage of parts in correct bins, not the percentage of parts picked correctly, because the robot might pick up the parts correctly, but then it may not place it into the right bins, right? So what we need to look into when we are trying to come up with performance metrics is the impact in the environment. It should correctly capture what impact we want in the environment. Similarly, for a refinery controller, the performance measure may be purity, yield, safety. For an interactive English tutor, an online tutor, the performance measure will be something like the student's score on the test, not how well the teacher teaches, because the teacher always may claim that the teacher is teaching very well, and we may come up with many metrics to prove that, but eventually a tutor's ultimate goal is to help the students score better on the test, right? So this should be our performance measure that it correctly evaluates the impact in the environment. In summary, in this chapter, what we saw is an agent is something that perceives and acts in an environment. We talked about an agent having sensors, actuators, and interacting with the environment. An agent function is, for an agent, is specify the actions taken by the agent in response to perceived sequence. We also discussed that performance measure evaluates the behavior of an agent in an environment. A rational agent is an agent that is expected to maximize the performance measure, given the perceived sequence it has seen so far. A task environment is defining four things, that is performance measure, environment, actuators, and sensors. And in designing an agent, we saw that the first step must be to specify the task environment as fully as possible.